What's up, guys? We are back with day 5 of Advent of Code 2023. Today was a brutal one. I spent a lot longer than I would like to admit trying to do this in AWK, and I'll go ahead and spoil the ending. I could not come up with the clever, efficient solution. Actually, I haven't looked it up, so I'm not even sure that it exists, but I feel pretty confident that there is one out there. So at the end of the video, I'm going to be abandoning my AWK code, and I'll show you my brute force Rust solution that took 2 minutes to get the final answer. But I got my 2 stars, and I'm going to show you how to do the same. So I'm not even really going to try to describe all of the rules today. I guess at a high level, it's not that complicated. You're given a list of seeds, and then each of these sections of the file defines a transformation on these seed numbers to eventually get locations. So you'll see we've got seed numbers. We map these seeds to soils. We map the soils to fertilizers, and so on until we get to location. And the final answer we want is, where does each seed go? So a seed to a location. Well, I guess actually I am going to say all the rules. Except I never remember which column is which, but one of these columns refers to seeds and one refers to soils. And then this is a range column. So this is saying something like 50 maps to 98, 51 maps to 99. And in this case, I'm not going to recite them all because there are 48 of them, but basically this is a range. You'll see in the AWK code I write, I usually call one of them, I think the second one is the source, so I'll call it SRC. I'll call the destination column DST, and then I'll usually call the range RNG. So that's about it for the first part. Let's go ahead and hop over there. All right, here we are in Emacs. You can see our sample input over here on the right, just what we were looking at on the web page. And today we've got a slightly more complicated AWK script. So you'll see, yesterday I was mentioning, we haven't really had to do patterns very much. But here we go. We've got a bunch of different patterns. The first one is just a nice regular expression pattern. So this is looking for a line, technically anywhere in the line that matches seeds, but you'll notice that this is the only place that seeds is. So this signals that we should parse the seed line. So as usual, we loop over the fields and we store them in this seeds array. I should also mention this is not the final solution. I've checked out what I committed and called the naive solution. This, if you try to run it, will use, it used like 29, 30 gigabytes of RAM on my computer before I killed it. So this is too naive, will not actually run and give you the right answer. And we'll see why in just a minute. But I wanted to say that first. So we get the seeds line. This could technically just be map because map only occurs in the second column. But I'll just put that, I'll put that back how it was. And as I've kind of mentioned here, this is checking that the second column matches map. So that's looking for each of these header lines. And when we see one of those lines, we set the state to whatever's in the first column. And we'll see why in just a second. Then we go on to the next line of the input because I don't want to parse this line after I've set the state. And then if we find a blank line, we just skip over that because we also don't want to store that in one of our maps. So now you'll see that in addition to regular expression patterns, we can do just plain booleans. So this is basically, it's saying when our state is seed to soil, then we call make map with seed to soil, which is an empty array. Same thing with each of these. So since we're calling all of those, let's take a look at our function make map at the bottom. You'll see that it takes an array and we declare a local variable I. So for I and 0 to $3, we are inserting all of these fields into our array. And this is where our memory disaster occurs. Because I thought this was fine. This script runs fine on the sample. But if we hop over to our input file, you'll notice that there's not just more input. The numbers are quite large. So what we're doing right here is constructing an array from here, adding this many numbers to it. So even just one entry has, 77 million entries. So that adds up quite quickly. And so that's 77 million. This is 56 million. This is 105 million in only 3 lines. Uh, so this approach did not make it very far. But I'll keep talking through it because the actual change to fix that is not a huge deal, and most of the logic remains the same. So after that, we make all of these maps, and then when we reach the end of the file, we just loop back over them and do our mapping. So you'll see this almost looks like some Lisp code here because we've got all these nested function calls. I guess we'll read it from the inside out. We initially call this get function, which in this basic implementation just checks if our index is in the array. If it is, returns it, and if not, it returns I. This is one of the rules I didn't actually mention on the rules page, but we've basically only got part of the map, and anything that's not specified in our file just maps to itself. So that's this in code. And you'll see that we just call it inside out. So we map S, seed to soil, then we call soil to fertilizer, fertilizer to water, water to light, light to temperature, temperature to humidity, humidity to location. This, of course, would have been very nice with OCaml's pipe operator. It would have looked a little bit better. But anyway, we've got that. And then I'm using one last feature I'm not sure I've used in these videos yet, but you can actually you can pipe straight into stuff. So you can use this for an output file. So if you want to write part of your output, you can use one of these kind of pipes. But you can also use just a pipe. And what we're doing here is we're going to print it into a numeric sort and take the top one because we want the lowest location. We're trying to plant the closest seed first, I think, is the story. So there we go. I'm not going to try to run this because it will never finish and might crash my computer. But after that, let's go ahead and hop over to the slightly less naive solution. Okay, now you can see that I've got the code still on the left, and I've actually left the diff up just to really draw our attention to the new part. You'll see that actually all I had to do was update my make map and my get functions. So if we jump down to make map, it actually got a little bit simpler. We just store the whole line, and then we move most of our work into this get method. Apologies for the indentation. I changed something with my tab width today. It's kind of thrown everything off. But you'll see that now when we call get, instead of just looking inside of the thing, we have to loop over it and expand all of the ranges ourselves. Except, again, instead of expanding them, we do a check where we just look if the thing we're looking for, I, our index, if it's greater than or equal to the first thing and less than or equal to the source plus the range. And if it is, then we return the destination plus this offset. So this is basically, if source is like the starting point of our range, then we need to know how far away from that we are, and then we add that to our destination. Because the source gets mapped straight. I should have drawn a picture for this, but source gets mapped to destination. So we need to know how far ahead of source we started so that we can take that same offset from destination. And again, if we don't find it in any of our positions, or in any of the ranges in the array, we just return what we were given. So this one will actually run, and this gives me the answer to part 1. And you can see that answer right there now. I was trying to see if I needed to preserve my compilation buffer, but I think I actually closed it earlier. So there's our answer to part 1. You'll see that it ran in 0.03 seconds, so really no problem with efficiency now. All right, let's move on to part 2. Okay, we're back over here at the rules again. This is actually pretty straightforward. It's a fairly small modification to the original rules, which are kind of the puzzles I like. We're told this time that each of these seeds actually is not a seed, but that we have pairs. So much like the other sections, this represents a seed, and this represents a range of additional seeds. So this actually represents the range from 79 to 92. Lots of a good recipe for off by ones in this challenge as well. So, as you might not see immediately, this makes things much, much harder. So let's jump back to the code again. Alright, we're back at the code, and as you can see, I even put in the commit. This is the naive solution again. And the nice thing about this is that you can see that not much has changed. So I did actually have an off by 1 error in the first case, but it didn't really cause any problems. So I did have to fix that just to pass the sample input. But other than that, all I really had to do was expand these ranges. So instead of having a single loop up here with seeds of I had to loop from j equals I up to j equals I to I plus 1 and store all of those seeds. But again, as we saw, this leads to, I called it like infinite memory usage in my README, I think. It's not infinite, but it is quite a lot. Basically too much to actually run. So again, this worked great on the sample, but I tried to run on the input, popped open htop, and I saw, like 70% of my RAM being used and the answer not coming out, so I had to kill it and move on. So after that, I'll go ahead and show you the pretty straightforward change that lets us use not infinite memory. Okay, and as you may have expected, the solution here is basically identical to the solution we made for part 1 to make it more efficient. Again, instead of expanding all of these, we just keep the seeds that we read in as a range, and we're using, of course, our hopefully well known by now string concatenation and awk to put them into one index. And after that, we just have to do this looping and splitting in our main function, or in our end block, basically. This time, yeah, I just went ahead. I have print x in here. I got rid of the sorting and everything because we never actually got any output for this one on the actual input. So this helped, but it didn't help enough. And so this is where I spent a lot of time trying to come up with a solution. I will go ahead and pull that up just to show you guys, where I ended up, but it didn't work. Okay, so I'm not really going to try to explain this one. I'll just kind of scroll through it. You can see the train wreck. So I had a piece of paper. I was drawing stuff out. I was trying to enumerate all the different ways that this could happen. Yeah, I had a lot of prints, deleting stuff, just really trying my best. Yeah, here's a diagram I drew in the code. So this is on GitHub. I went ahead and put it up. I think the commit says something like final mess of awk that I ended up with. We got our classic min and max functions. So I could not get this to work. I'm not going to go through the code like I said, but I'll try to kind of explain what I was going for. I guess I actually wrote it in the code as well. But it seemed to me that instead of performing all of the transformations on all of the seeds, what we wanted to find is just the closest seed. So I thought possibly that turning around the maps and starting from the locations could actually make things cheaper. I think that kind of approach works a lot of the time, where, yeah, instead of considering every seed, you start from the location. Now that I'm saying it out loud, it doesn't sound quite as promising, but that's what I was trying to do. I also thought that would allow you to operate on ranges the whole time, so that you could iteratively transform the ranges, and then by the time you got back up to the seeds, I thought that maybe you would be able to, dramatically reduce your search space and then loop over those final seeds, basically. Something like that. Like I said, I still haven't, checked on Reddit or anywhere for one of the good solutions. So that's what I was trying to do in awk. I guess after that, we'll just hop over to the Rust solution. Okay, so let's take a look at this Rust solution. So you'll see I've pulled up again on the right hand side my naive. Is this my naive awk solution that was running too slowly to actually finish, and I just transferred it to, Rust. I thought this might be somewhat interesting to compare and contrast the two. So one of the things this will help to emphasize is how many automatic things awk does for us. So you'll see in the Rust version, I have to initialize all of my vectors instead of just dreaming them into existence over here, actually including seeds. I have to actually read the file. I decided to use include stir. You could just use read to string. This sounded like kind of fun. Let's see, we have to initialize our state variable, and then we get down to the loops. We have to actually do the loop ourselves. What a burden we have. And we also have to split the line ourselves. So there we go, looping over the lines, splitting the lines. And then we also do our if statements. We got all these if, else ifs, instead of this nice pattern action kind of syntax over here. So that's all we're doing here, parsing all the lines. Yeah, this much Rust, this much awk. Basically the same, but a little bit more verbose on the Rust side. Okay, so once we do that, it's pretty much a one-to-one translation. So this is a trick that I don't particularly like to do, but if you're doing like a minimization or a maximization over something, and what I usually like to do is use the first element as my starting value. So in that case, because you're using an actual piece of the data as the initial value, you know that you're going to get a reasonable answer. So one common issue you can run into, let's say let mut min equals 0.0, right? If all of your numbers are positive and not 0, you'll actually get a minimum that is not in your data set. And things like that can happen for other numbers as well. Probably where I've run into this the most is letting max be 0.0 and all of your numbers are negative, in which case you get 0.0 as your max. So one way around that is just to use the maximum or minimum number available for the size. So if you're minimizing, you want to use the max, and if you're maximizing, you want to use the min. Yeah. So anyway, we initialize our search variable, and this is actually an additional optimization. So I'll talk about that in a second. But everything else is just a one-to-one translation. So for is in this, I had to loop over. Did I check out the wrong version of the code? Yeah, I think I checked out the wrong version of the code. Oh yeah, this is the version where I was putting everything in seeds. But you get the idea. So we're looping over the start to the end of our seed ranges, and then our x is just the same. Get this, 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 this. And we've got the same kind of functions down here. We've got our get, should look pretty similar. It's so nice to destructure things like this in Rust though. Whereas in awk, I had to do something like this, split and then unpack it manually. Otherwise, pretty much exactly the same. This is the same, this is the same, this is the same. Minus the parentheses around the this expression. And then make map as well, pretty nice, except I've got an assertion. And again, I'm using tuples instead of packing everything into an array. So there we go. Get. We've got references, whatever. And what I did try to do is put all of these into res. And then down here I called res.sort, debug res0. And I was watching it run. It got through all of the seeds, and then it just hung while it had to try to sort the whole thing. And if you look up the documentation for Rust's sort, on slices at least, it says it can use up to an additional n/2 space. So basically I was using 1.5 times the res vector's length in elements, in U sizes. So that was taking quite a long time to sort. So I decided to just do the sort myself by maintaining a minimum value. So with all of that done, I'm not going to run the code. It does take exactly 2 minutes to run in release mode, but I was happy with that after a very long time of toiling over the awk code. So let me know in the comments down below, how did you guys fare today? I thought it was pretty challenging. That seemed to be kind of the consensus on Reddit, but like I said, I didn't look too closely over there. Anyway, I'm glad it's over. It's got me a little scared for the coming days, but I haven't said it in a while, so be sure to like and subscribe. Let me know if you want me to keep making videos like this, and I'll see you guys tomorrow, hopefully. Bye.